Okay, we should be live. Welcome to another
Yeah,
live
this is
of,
better.
well, introduce the thing. Welcome to another live for the Assumption of Physics project. Today we have Rudra that is gonna talk to us about his research. What happened is that he wanted to participate in the school a few weeks ago, but he couldn't because he had another conference. And then I looked up the conference, what he was presenting, and what he was presenting is actually related to one of the open problems that we have of trying to characterize what happens to uncertainty in symplectic spaces, and therefore phase space and on positional momentum. And it turns out that there is a very old theorem actually about it that has been somewhat forgotten. And Maurice de Conson recovered it and made him aware, and then Rudra is doing some stuff with it. So let me just pass it to Rudra, and please tell us about all this stuff.
Yeah, thank you for inviting me. I'll share my screen. Okay, can you see it?
Yes, I just need to check. Yes. Can you make it more like a format the yeah, that should be better. I'm just seeing how it's streamed over the internet. Okay, go ahead.
Okay. Okay, so the the main topic that I want to talk about is essentially the central result of my paper in collaboration with my collaborator, Dr. Hemant Kumar Mishra. And I'm gonna give you some sort of like outline or at least the machinery that I used, and I think that might appeal to many people on here. So first of all, I define what a quadratic form is, which is just a map from the vector space, which in our case is going to be real and finite dimensional, satisfying two criteria of homogeneity. Say if you have q of cv, you get c squared q of v, hence the term quadratic, and you have a polarization identity. You could have started with the polarization identity and also then in the definition would come across quadratic forms. So they're essentially equivalent to each other. Many textbooks, they'll start with these bilinear forms and then go to quadratic forms, or start with quadratic, go to bilinear. Either way works. And there's a notion of positive semi-definiteness on our quadratic form. So if q of v is greater than or equal to 0 for all non-zero vectors, then it's called positive semi-definite quadratic form. In the case of this abstract notion, we have a nice example. An n by n matrix A defines a quadratic form on Rn, the standard vector space, by x goes to x transpose Ax. It's the very simple example we will encounter in linear algebra. And of course, you can choose a basis, and then you have this equivalence between quadratic forms and symmetric matrices. So if I fix a basis, I can write my vector as a column vector in the components with respect to that basis. Q of V then becomes this matrix product V transpose the matrix phi sub Q times V, where V is, again, as I said, the column consisting of the components in that basis. So we can either talk of quadratic forms in an abstract basis free way, or you can also talk of matrices, because the main Williamson's theorem, I think Williamson was applied mathematician, so he worked mainly in matrices in his original 1936 paper. But when I discovered the result first in my undergraduate thesis with my advisor, we used this abstract notion of vector space, these quadratic forms, because my advisor was a pure mathematician and not applied.
Yeah, I prefer the matrix form because when you talk about covariance matrix, which is the thing that I'm interested in, you really think about a matrix, not a bilinear form, or like not a quadratic form.
Okay. There's a little bit of advantages with this approach. I will probably talk about that a little
Good.
bit later. But uh, just like we can diagonalize a symmetric matrix. Again, the matrix we have here is symmetric. Um, there's a diagonal form of a symmetric matrix. There's the sense of a normal form for quadratic forms, which is sort of the little more general notion of what it says is if you have a basis, then Q is said to have normal form in the basis if Q of V for any vector is a quadratic polynomial in the squares of the coordinates. So that means you're going to have in normal form quantities like x squared plus 2y squared. You're not going to have cross terms. And that's why I emphasize squares. And so with the last example, x transpose AX, it's in normal form in a basis where A, the matrix here, the symmetric matrix here, is in diagonal form. So diagonalization and diagonal form or normal form are equivalent notions. There's a spectral theorem that we love in quantum mechanics, in classical mechanics, that any symmetric matrix can be diagonalized using an orthogonal matrix K, such that K transpose the matrix K is equal to a diagonal matrix with eigenvalues on the diagonal. Is well established classical result, and this is what we sought, my collaborator and I sought to do with the symplectic version of a diagonalization theorem. So that's it for the basic linear algebra. Here's a little bit of a symplectic twist, as I like to say. So again, V is a real vector space. We are defining a bilinear map from V cross V to R. It's called a symplectic form on V if it satisfies two criteria, very importantly, that it's anti-symmetric in its arguments. So omega uv is minus omega vu, and it's non-degenerate. So omega of uv equals 0 for all u in V implies that V has to be the zero vector. I would say the second one is a little more important because sometimes you encounter a pre-symplectic form which is degenerate. So again, so naturally, no surprises. Vector space equipped with symplectic form is a symplectic vector space, and it's well known. You can show not so difficultly that it is even dimensional. And we have a notion of a symplectic subspace. So a subspace of a vector space is symplectic if omega restricted to that subspace, so W, is also a symplectic form, and you have to check both the criteria again independently for this restriction. And just like we have an orthogonal subspace in the classical linear algebra defined with respect to an inner product, we have an analog, a symplectic analog. It's called a symplectic complement. So it's all the vectors in V, which say assuming we have already a symplectic subspace W, for all vectors U in W, we're taking the vectors in capital V such that set the symplectic form to 0. This is essentially quite similar to this notion of orthogonal subspace in the classical case. And
Let
again,
me
you
ask
can
you
check.
one thing.
Yes,
Typically, a symplectic form should also be closed. You are not requiring that because it's
it's
unimportant.
finite dimensional, and yeah, it's essentially because it's finite. I mean, I think that notion of like a closed symplectic form is when you have like a two form. For I think so for simple vector spaces, it's isomer. The two forms are
Oh, because we're on a real vector space, we're not on a manifold.
yeah,
That's the idea. Okay.
yeah, exactly. Because in a manifold, you have to do it locally in the
Yeah,
tangent
yeah. Okay.
space. Okay, as I was saying, you can check that this symplectic complement is also a symplectic subspace, again, satisfying this definition one. Just like we have a notion of orthonormal bases for classical linear algebra, there's a notion of symplectic bases. So quite simply, again, let V be a two n-dimensional symplectic space. A basis P1, Q1, Pn, Qn of V is a symplectic basis which satisfies for all ij from 1 to n. Omega of, so any two p's in the omega and any two q's in the omega will give 0. And only omega of pi with qj will be 1 when I and j are 1. That's what this Kronecker delta means here. So think of them as sorry, give me a second. Yeah, sorry, yeah. So the p's, you can think of the canonical momenta from Hamiltonian mechanics, and the q are the positions, canonical positions. So this essentially gives us the Poisson bracket structure is analogous to the Poisson bracket structure in this setting. We're gonna need all these, at least I needed it in our paper. Very important machinery. And a standard symplectic space, an example of that is R2n. Just like, I mean, you have the standard inner product on R2n defined by X transpose Y. You can think of that as having an identity in between. So X transpose like identity times acting on Y. We just replace the identity by this standard symplectic matrix J. So X transpose JY is going to be our symplectic form in that case, where J is defined like this. IN is the n by n identity matrix. And you have nice bases. So standard basis of R2n is also a symplectic basis. And you can check with the standard inner product, it's an orthonormal basis. You also have a symplectic basis which is non-orthonormal, which is given by this 2, 1, 1, 1. So these are very simple examples. R2n essentially, encapsulates all the properties you need to know about symplectic vector spaces, again, because they're vector spaces. Now the main beast, the elephant in the room, Williamson's theorem. So again, let me first explain it in the matrix form, which is going to be more popular anyways. So the standard symplectic matrix I defined before, given by J. We have a notion of a symplectic matrix. So an n 2n by 2n real matrix M is symplectic if M transpose Jm equals J. This symplectic matrix is the symplectic analog of an orthogonal matrix. Just replace the J by an identity and you get the notion of an orthogonal matrix, which, or in other words, a matrix, a transformation that will preserve the inner product. In this case, the inner product is given by the symplectic form. So the theorem says, and this is the analog of the spectral theorem, I must add, a symplectic analog of the spectral theorem is for every 2n by 2n real symmetric positive definite matrix A, there exists a symplectic matrix M such that M transpose AM equals D00D, where the D is a diagonal matrix with whose entries we can, with the analogy, call symplectic eigenvalues of A. That is the big theorem. This is quite like spectral theorem, except we have to take positive definite matrix. To be honest, the original paper from Williamson had considered any arbitrary symmetric matrix with no additional structure. So he didn't assume positive definite, semi-definite, anything like that. But the problem when you do that is this D that you're getting is no longer going to be diagonal. Sure, this final matrix will be block diagonal and will have blocks D and D, but this D in the block is not going to be diagonal for arbitrary symmetric matrix. Only for positive definite and positive semi-definite, you're actually going to have D to be diagonal. This has to do with the fact that when in the proof of this theorem, you consider J times A. You consider the eigenspace of J times A. Even though A is symmetric, it's diagonalizable. J times A is not necessarily diagonalizable. So the loss of this or the diagonal property of D is because of losing the diagonalizability of J times A. And now I will explain why we need J times A. That's the beauty of the machinery we have tried to describe in our paper. Because when we talk of quadratic form, we came across the Williamson-Hormander theorem. It's Williamson-Hormander because Hormander gave this form in terms of quadratic forms and not matrices. But with the term machinery we have, the proof is a little easier in this quadratic form language. So V is a 2n dimensional symplectic space. Q is a positive semi-definite quadratic form. And note that we're doing a little better than the Williamson I stated on the page before. We're considering semi-definite, not definite. You can, of course, recover definite as a special case of this, but let's talk a little general. Q reduces to a normal form in a symplectic basis, P1, Q1, Pn, Qn. There exist non-negative integers KL and positive numbers mu1 through mu k, which are going to be the symplectic eigenvalues, such that we have decomposition 5. So I've taken an arbitrary vector in this symplectic vector space, given this existence of the symplectic basis, and I'm saying that this decomposes our Q into this symplectic eigenvalue sector. There's a K of those, and since it's semi-definite, you're going to have this sector which is unpaired from, there's no Y term here, from K plus 1 to K plus L. So the symplectic eigenvalue on this is 1, and the corresponding symplectic eigenvalue on the Y for that is going to be 0. That's it. There's going to be that unpaired sector just because we've considered a positive semi-definite quadratic form. Notice this sector is paired. That's why we call these sort of the principal symplectic eigenvalues. There's 1 here and a 0 on that corresponding Y, and then the rest of them from K plus L to N are just going to be 0 eigenvalues, because that part comes in the kernel of the quadratic form Q. It's semi-definite, so it has a non-trivial kernel. So we call the above normal form a symplectic normal form, and the special case, of course, with positive definite, you'd have K being N, and then you wouldn't have the second term. The special case is, and this is what we've tried to sort of extend in the paper, is if kernel of Q is a symplectic subspace itself, then this L is 0, and you have this some non-zero symplectic eigenvalues here from 1 to K, and then from K plus 1 to N, you're going to have 0 symplectic eigenvalues, but in this special case, they're going to be paired at least. Notice how this was not paired. There was no yi squared term. They're going to be paired with the when the kernel is a symplectic subspace. That's what's different. That's the extension we can do, which sort of preserve that diagonal property of that D matrix. Again, going back to the matrix form of Williamson's theorem. Before I do that, why are we interested in this? The applications of symplectic normal forms, which the journal I submitted to says are straightforward. Anyways, Hamilton mechanics, when a system's Hamiltonian is a positive semi-definite quadratic form over a symplectic space, then you can decompose your system using a symplectic transformation, because we know that the symplectic normal form exists. There exists a symplectic transformation that will decompose the system into independent normal modes. And since it's symplectic, it will preserve the physics of the system. It will preserve Hamilton's equations of motion. So, and also the determinant is +1. So you really are not distorting or changing the orientation of your phase space at all. And in quantum optics, you have Gaussian states. I can see many people's faces light up when I said Gaussian states, completely described by its mean vector and covariance matrix. You can symplectically diagonalize the covariance matrices because I think they're positive definite. And you'll get a tensor product of thermal states, which are easy to deal with on their own. You have these independent products. The systems essentially decompose nicely. In more mathematical applications, in symplectic topology, it facilitates an immediate proof of the celebrated Gromov's non-squeezing theorem, at least in the linear case. Maurice de Gosson, in his book, shows that you can get uncertainty principle using Gromov's non-squeezing, and I think that's like his like one of his biggest achievements. Um, Statistical mechanics. This is something I've tried to look into. Didn't find many good resources. The partition function of a gas of n identical particles in d dimensions. If it's given in terms of n quadratic forms, the Hamiltonians are given by n quadratic forms on R 2dn, because that is the phase space, and your partition function is going to be exponential of minus beta h. You can decompose your system again and evaluate the partition function. Eases the computation. Okay, now this is the main result of the paper is we had the simultaneous diagonalization theorem in classical matrix analysis. So if you have two matrices which are diagonalizable and they commute with one another, then you can simultaneously diagonalize them in a common orthogonal basis for symmetric matrices, of course. That was the classical result. We use that in quantum mechanics for, I think, complete commuting family of observables, for example, uses that. We asked the question, is there a symplectic analog to Williamson's theorem? So can we have a notion of simultaneously diagonalized in the sense of Williamson's theorem? That is by using, does there exist a common symplectic matrix that will diagonalize two positive definite quadratic forms? The algebraic condition for that is not so straightforward. Here in the top, in the classical case, you needed a commutator to vanish. You needed AB minus BA to be 0, the commutator of AB to be 0 for that to be true. In this symplectic case, you can't, that doesn't work. You have to consider the commutation of something that's called the Hamilton maps. So if you remember what I had said before, I had said we have to look at the eigenspaces of the J times A, where A was that symmetric matrix. J times A was the Hamilton map corresponding to matrix A. There's a more abstract notion of this, is if the Hamilton map is essentially a bridge between the anti-symmetric world of this symplectic form and the symmetric world of the symmetric bilinear form. So the bilinear form phi q that corresponds to quadratic form q is symmetric in its arguments upon requirement, and omega is anti-symmetric. So HQ, the Hamilton map with respect to quadratic form Q, is sort of the bridge between both of those. In symplectic geometry, I think it is called the Hamiltonian vector field, corresponding to. Yeah. So the only thing is we've, I think, dropped a factor of 2 for the quadratic form, because when you take the derivative of that, you get a factor of 2. We've just sort of dropped that. So and you have the nice algebra homomorphism between Poisson brackets and the commutators of these Hamilton maps. And this all comes because, as I said, it's a Hamiltonian vector field. You have that nice algebra homomorphism between the Poisson bracket and the commutator of the observables. Of the Hamilton maps. So this is how I'm defining the Poisson bracket. It's in the usual sense with respect to some bases. The Poisson bracket is strictly not needed for the main result of our paper, because You can just formulate everything in terms of the Hamilton maps rather than the Poisson brackets of the quadratic forms, but they're equivalent because of the algebra homomorphism. That if I have the vanishing commutator, then I have the vanishing Poisson bracket as well. And here's the main result. So if Q and R are positive semi-definite quadratic forms on symplectic space V such that the kernels of HQ, HR are symplectic subspaces of V, then we have that Q and R are reduced to symplectic normal forms in a common symplectic basis if and only if two criteria. As I said before, the commutator of HQ and HR must vanish, or you can say the Poisson brackets of Q and R vanish, they're equivalent, and that the kernel of HQ intersect kernel of HR is a symplectic subspace. The second criteria is important because just because we stipulated at the start that the kernels of HQ and HR are individually symplectic subspaces, that doesn't imply that their intersection is also a symplectic subspace. This has to do with the problem of degeneracy. What if the omega restricted to that intersection is degenerate? So we never know. That's the problem when you're doing symplectic geometry. You quotient your symplectic manifold, but you don't know the quotient manifold is symplectic itself. So you have to enforce this condition. We've generalized this to an arbitrary many family of positive semi-definite quadratic forms, and it's safe to say cannot be extended any further because you change you change the positive semi-definiteness to some arbitrary signature, and you lose the diagonalizability of the HQ, and then your D from Williamson's theorem is no longer diagonal. The point is you get a Jordan block for HQ, and Jordan blocks can't be simultaneously Jordanized. There's a counterexample for that. You can do that if HQ is diagonalizable, but when you change the signature a little bit, you make it hyperbolic with one negative inertia and rest of them positive, you lose the diagonalizability of the HQ, and then you can't use condition one to extend further because you don't have a simultaneous Jordan block theorem in classical
Let me ask you
analysis.
one thing. So you said that
Yes,
the HQ and HR in symplectic geometry becomes the Hamiltonian fields. The
vector,
commutator
yes.
is the Lie bracket between the two?
Yes, exactly.
Okay.
Exactly. That's why we have the homomorphism, because if you go back because if you go back to the definition, the HQ is going to be the interior product of
Yeah. Mhm.
like you have to so if you have a function f, the df equals interior product with some x of omega, and that x is becomes the Hamiltonian vector field corresponding to the one form df, for
Yeah.
example, and then you essentially recover the algebra homomorphism from the definition of the Poisson brackets in terms of the omega. Yeah, so the forward direction is simple. It's a follow your nose. Assuming you have a symplectic basis, you just get the decomposition for Q and R because it's symplectic basis, which is going to simultaneously normalize it, and you can check that we satisfy condition one and condition two given such a basis. That's very simple to do. Either check the Poisson bracket vanishes or HQHR vanish. And you can also check kernels intersect to give a symplectic subspace. That's the forward direction. The backward direction, I would say, is similar to what we do for the regular Williamson theorem, except people don't do it in the context of quadratic forms. They do it in terms of matrices, which is very nice intuitive proof. But this has a little bit of a power because that method doesn't fails when the signature is positive semi-definite. This general method works in that case. It can get a little complicated when you change the signature, but it's the same induction over dimension argument. So so now we're going from the reverse direction. Suppose the commutator vanishes and the kernel intersect to get in a symplectic subspace. We will just construct a nice symplectic basis. So consider W, which is the symplectic complement of the intersection of the kernels, which according to our definition is also its own symplectic subspace in its own right. And you can check its invariant under HQ and HR. Then there's a lemma that HQ and HR are diagonalizable on the complexification of W, such that given that Q restricted W and R restricted W are positive semi-definite, then since they're diagonalizable, use the classical result and find a common eigenvector, because we know that they commute, so we can find a common eigenvector in complexified W. That's a complex, that eigenvector can be expressed as U1 plus I V1, where U and V both belong to capital W. And then just take the real and imaginary parts of V and W. And then you just have to show that the omega of real and imaginary parts is non-zero. Normalize it so that it satisfies the normalization property of the symplectic basis that we defined earlier. And the span of that P1 Q1 is going to be a symplectic plane, two-dimensional. And then just repeat this argument on the symplectic complement of this span. So that's an inductive argument until we exhaust the dimension, where until k equals half the dimension of W. W is symplectic subspace, has even dimension, so 1/2 the dimension always makes sense. And that's it. You've found a symplectic subspace for W. Very nice. And you just combine this with a symplectic subspace for W per symplectic complement, which is just the kernel's intersection, which we said at the beginning is a symplectic subspace. So we can always find a symplectic basis or a symplectic subspace using a symplectic Gram-Schmidt sort of algorithm that's Maurice de Gosson gives in his book. And through this process, we have checked that this eigenvalue that we had here corresponds to the symplectic eigenvalue. Just drop the I, and that's why we're getting this nice set of equations. So it wasn't just an arbitrary symplectic basis. The symplectic basis actually is giving us a nice decomposition as well. So we found the decomposition and the symplectic basis that completes the proof in both directions. The matrix form of this is important. As I said, the Hamilton map is given by J times A, where A is a symmetric matrix. So the condition becomes a commutation of the Hamilton maps, or a commutation of JA and JB, where A and B are symmetric matrices, which is exactly equation 9 here. Just add a J on the left side, and you get the commutator of JA and JB being 0. This you can call symplectic commutativity of A and B. That's essentially the matrix result of the main result. And it was
So
nice because
going to what you were saying before, that condition to look like would become the orthogonality condition in the standard non-symplectic case, where you would have an identity for the J, right?
yes, exactly, precisely, yeah. So that's the analogy. That's why I started with comparing with orthonormal basis vectors and things, because just change the J to I, your symplectic inner product becomes their standard inner product,
Right.
and AB equals BA, and that's the classical result. So it's a kind of a generalization in that sense. This was nice because again, I'm saying this is a preprint, recently got rejected, like right before I came here for the journal, but we got a sanity check, and I don't think anyone has any problems with the sanity check that A's are, we got that a 2n by 2n real symmetric positive definite matrix A is diagonalizable by an orthosymplectic matrix in the sense of Williamson theorem, if and only if AJ equals JA.
Okay.
So B, just set B to the identity and Bob's your uncle, as they say in the US.
Yeah.
Orthosymplectic in this case is orthogonal and symplectic. It's isomorphic to, I think, the unitary. Just change your field from the reals to complex and complex to orthosymplectic is related to the unitary. There was a corollary. What about so if A and B symplectically commute, what about their powers? Do they symplectically commute? For distinct powers of A and B, here's a counterexample to tell us that they don't. Okay. What about same powers? Maybe they do. They don't. I spent a week on Mathematica constructing this counterexample. For 4 by 4, you can't. There's no counterexample in 2 by 2. 2 by 2 is very simple. In 4 by 4, there is. So even the same powers don't symplectically commute. So what more algebraic conditions do we need is the question. Well, we have symplectic commutativity. The only thing that is missing in this entire drama is the regular commutator. So 2n by n real symmetric positive definite matrices A and B commute as well as symplectically commute mutually. Then their powers also symplectically commute mutually for all S belonging to R. And here's a short proof of this, which used the sanity check result from before. Yeah.
So wait a second. The only change is that you are positive definite instead of positive semi-definite?
Yeah, because I mean the problem with this proof is we've taken the inverse. So positive
But
definite
that's the only
works.
requirement that you need. That's it.
No, and that they should like commute as well, like commute
Oh,
classically
they're
as well
commuting
as
is that.
symplectically.
Okay.
Yeah. That's why the algebra becomes so much more easier.
Okay. Is
The
it an if and only
applications.
if, or is just a condition?
Uh, no, I think it's one
It's just one way.
sided.
Okay.
Yeah. Applications, and this was something I struggled with. It was a math heavy paper. I mean, I have a degree undergrad in math, so they expected me to be a little more mathematical, but I'm always drawn to physics applications. I said, how can we generalize? I didn't find any systems where they would consider this simultaneous covariance matrix decomposition. Maybe this will be this might be useful for the assumptions of physics that if you have two n mode bosonic Gaussian states, rho and sigma, with corresponding covariance matrices, then they can be simultaneously decomposed into a tensor product of n single mode thermal states. Again, if and only if satisfying the criteria of the main result, the theorem. And again, with statistical mechanics, you can also, if you have a Hamiltonian, which is quadratic and also satisfies the symplectic commutating property, then you can find a nice common symplectic diagonalizing basis. And the future scope of this is, and this is the reason why I haven't written another paper, is to extend this to the infinite dimensional symplectic vector space. I know two papers which do Williamson in a product Hilbert space, H cross H, for example, by I think Gajendra Babu. I have them if anyone's interested. The main thing is to ask, can we extend our result from the paper to infinite dimensions? Because mind you, there's a different symplectic has a different notion in infinite dimension. There's a weakly symplectic and a strongly symplectic depending on the surjectivity of your of that symplectic form.
I
So you have to
haven't
define.
seen a good unified treatment of infinite dimensional symplectic. Uh, okay. Yeah, no, but it should be symplectic vector space. So, for example, do you know how to handle in field theory the fact that you have infinite dimension and you still have some type of Poisson brackets on the fields and so on? I have never seen a symplectic treatment of
No,
that.
that's the struggle. So I mean, so the area I want to do my PhD in is actually exactly that stuff. Is how do we use like the symplectic framework, this geometric framework for field theories and other kind, because if, like the problem with field theories is it's continuous. It's not like just countably like infinite, or
Yeah.
you can. it's a continuum, and like that entire mathematical analysis, I haven't found very good references. There's different kinds of treatments. There's a Bayesian quantization. There's different kinds. But I think what for example, Professor Christian Zeiman at Heriot-Watt University does, he looks at polysymplectic like quantization. So polysymplectic is in QFT, you consider time as a special quantity, like you define your momentum with respect to like derivation, differentiation with time. Like you have part like variation of the Lagrangian with respect to like a q dot, for example, that becomes
Yeah,
your
but I'm even
momentum.
talking about classical field theory, not quantum field theory. Just standard classical field theory. So electromagnetism, right? That in
Yeah,
principle should have a symplectic treatment, and you don't have the problem of quantization.
no, yeah, there hasn't been one. There's no, not that I've seen at least. I mean, if anyone, I mean, that's the point of like the reading stuff, is I want to build my level. I haven't done much infinite dimensional vector spaces on my own, as so I have to first do that, and then maybe in the future I hope
Yeah,
to
yeah, but
do
so
something.
just to tell you that's an open problem that I'm very interested in, because one of the related problem is how do I basically do information theory on spaces of field configuration, and even that I haven't seen. I haven't seen it done. The fact that I haven't seen it done doesn't mean that there isn't somewhere someone that is doing it, but I haven't seen it, and I
It's
need.
obscure, yeah, it's
Yeah.
obscure. I haven't seen it either.
Yeah, so if you ever see something, or if you have results, or if you want to
Sure,
talk about those things and so on, I'm very very interested, because it's
sure,
we
sure.
have all these results of the geometric interpretation of the action principle and all that we have for finite dimension, and I need some type of symplectic treatment to be able to transfer to essentially the continuously many degrees of freedom. That's basically.
Yeah,
Yeah.
yeah,
Anyway,
yeah,
Christine,
yeah.
did you have a question or you change your mind?
No, no, I don't have a question.
Okay. Okay, please go ahead.
So I mean, there was one guy who reached out to me. I think someone named Baumgarten, some postdoc, who does that like relativistic mechanics, accelerator physics. He said there's something called as an electromechanical equivalence principle. So that's where like the symplectic stuff might be of use. And then when I went through it, I realized, well, actually the gamma zero matrix from our Clifford algebra, gamma zero Dirac matrix, is actually the same as J. Both of them squared to give minus identity. So there might be some stuff there. I'm not too confident. The last one I was absolutely not confident about. It was if you have a system with quadratic integrals of motion, any system near its equilibrium point can be written, expressed, analyzed by Hessian, which is a quadratic form
Yeah.
or bilinear form matrix, which you can analyze using its symplectic eigenvalues instead of the classical ones. Advantage of, again, the symplectic emphasized because it preserves Hamilton's equations of motion. That's the only examples I could really think of. I wrote to many people, didn't get many good responses. So uh, thank you. That's the link to my paper if anyone would like to read the. But I must say that the senior thesis I wrote had way more details. I actually went through the hyperbolic case, not just the semi-definite case, with my advisor. It's very detailed linear algebra. So yeah, if anyone has any questions, I'll
Yeah,
be
so
here.
I want to see how I can use these things for the things that I want to do. So I think there are two things. Let's see if I should write them down both before I remember. One is essentially understanding how the sort of the uncertainty, the evolution of the uncertainty. And then there is something else that it's sort of how to relate the sort of the symplectic geometry part of classical mechanics with the Riemannian part. And we can talk about that later. So the first thing is what we basically have and in in the classical case, for the 1 degree of freedom, we recover the uncertainty principle by essentially saying I have a minimum of entropy. And if you have a lower bound on the entropy, you basically find that you also are going to have a lower bound of the uncertainty. And very simply, what happens is that if you fix the uncertainty, which in this case would be fixing the determinant of the covariance matrix, then the Gaussian is the distribution that maximizes the entropy. So now it works in the other way around. If you fix the entropy, the Gaussians are the one that minimize the uncertainty. And then what's going to happen is that since now you have a Gaussian on phase space that's fully defined by the covariance, by the determinant of the covariance matrix, and then the uncertainty on position and momentum, the product of the two, becomes minimized where you do not have a covariance when the things are uncorrelated, and therefore the determinant of the product, the determinant of the covariance matrix is just the product. At least this is for 1 degree of freedom. Now, what I'd like to do is sort of generalize this idea. And what I'd like to understand is essentially what happens if I just start, let's say, with a covariance matrix where the uncertainty in each degree of freedom is the same. So basically, this corresponds to the diagonalization that you have in Williamson, and that D is not just a diagonal matrix, but it's the identity times a number. This means that I've spread the uncertainty equally in each degree of freedom, but it also means, again, when we are going to do the extremization of the entropy, is that I've also spread the entropy equally in each degree of freedom. And this is where I want to start, because the idea is that if I put a lower bound on the entropy, I have to put a lower bound on the entropies of all the marginals. Because it's not that I have 0 entropy for the total and I have -1 entropy on 1 degree of freedom and 1 entropy on the other, such as the sum and then 0. So the reason why you would have the uncertainty principle now becomes stronger, because you do not just have a lower bound on the entropy of the system in general, you have a lower bound of the entropy of each independent degree of freedom. And the conjecture now is, or at least what I like to understand is how this physical requirement becomes a bound on the covariance matrix. So I'm not really interested in taking a random covariance matrix and know that they can be diagonalized. I know that I start with a matrix that it's diagonalized already, and where these are essentially identity times a constant. And I want to understand what is the space of covariance matrix that you can reach through that, and then find uncertainty bounds that would give me sort of an extension of the uncertainty principle to an n-dimensional case. Does that make any sense?
Yeah, I think I got the gist of it. So since we're concerned with covariance matrices, we're basically looking at symplectic eigenvalue, or how the symplectic spectrum is structured, or what are the the inequalities that the symplectic spectrum satisfies, essentially.
So we already know what the symplectic spectrum is, because it's going to be the one given by a diagonal matrix that is actually an identity times a constant. In fact, for our purposes, we can even think that the constant is 1, and so that the diagonal matrix is actually the identity.
Okay, yeah.
Like,
So
it's
you're
going to be
looking
h
at
bar, right? But that doesn't really matter. It's a constant. And then I basically need. Go ahead.
No. So you're going to look at like the lower bounds on each of those sectors. sadly.
Right. So ideally, like my intuition should be that I should be able to take my covariance matrix and form a block diagonals that are, Q1, P1, Q2, P2, QP3, P3. And in the diagonal, you see the uncertainty that it's inside each degree of freedom. And the off-diagonal term, they become how much the two degrees of freedom are correlated, right? Because it's the covariance. And my suspicion is that there are going to be parts that basically stay within these blocks, and then parts that move things around the block. Because if you imagine your J exactly as you have it there decomposed, you see that there is an identity times the symplectic, within the degree of freedom. And so within the degree of freedom, you're basically kind of doing an area product, but across degree of freedom, you have that identity. And so I would kind of expect, if I look at how this thing evolves, you should have some kind of symplectic transformation within the degree of freedom and some kind of rotation across the degree of freedom, such as you can take, the uncertainty of one degree of freedom and move it in covariances and then move it around. That's kind of my intuition that could be completely wrong. But that's kind of what I'm trying to understand. If it's
So
possible
if you have
to.
Williamson theorem, which will like decompose your system, and then you're looking to like restructure. So you can always restructure without changing the symplectic spectrum by using like or orthosymplectic transformation. Essentially, you can move like the blocks because it's unique up to like this reordering permutation sort of matrix.
Right.
and then and then you want to look at there's many types of like factorizations of symplectic matrices. I think Gosson does a good job of giving most of him in his book. You want to look at like how that symplectic matrix, which is diagonalizing your covariance matrix, is factored in terms of like those product of those factorizations. So I think one of them could be like the rotation, or like I think there's like a squeezing transformation that I think they call in quantum information. So that kind of you can then probably you can look at like what different factorizations your symplectic matrix is actually consisting of, and then analyze those sort of operations.
Okay, so could you, like, I guess I'm not familiar with this type of factorizations, so I'll probably
There's
have to.
there's a few like I think there's like there's an upper triangular factorization, say for like a GL
Yeah,
matrix. Like you
I don't
can
think.
write it as a product of like upper triangular, like any matrix can be written as a product of like upper
Oh, yeah,
triangular and
okay,
lower
yes,
triangular.
yes, yeah.
Yeah, that kind
Okay.
of. So there's many types of factorizations for the symplectic transform, just specifically for symplectic ones.
Okay.
I think there's like one that's called Ikawa or something. Gosson does a good job of writing it all in his book.
Okay, so you
So
basically say I should go and look at his book, see what pieces are there, and then
yeah,
see
yeah,
what
definitely.
was.
That's the best place to start because he writes in a very balanced way. He writes not too mathematical. He's connecting it always to like quantum mechanics in the book applications to quantum mechanics.
Yeah, I'm actually just wanted to do it in classical mechanics because I need the certain
Okay.
principle. There is a comment on the chat from Tom. It says, I was disappointed with Bertrand Russell's position on projective geometry and gave up on studying symplectic geometry. So the problem is of these type of things that become very abstract and if you don't have an anchor in the physics, for example, I started understanding and appreciating symplectic geometry when I first started essentially trying to understand the physics of classical mechanics there. And also when I started rewriting it in terms of component notations like we do in general relativity, because then I could extract the physics out, and it was only then that we were able to get the physical interpretation of the action theorem because I did all that reverse engineering. So the problem is always that the math now is very far from the type of intuition that you would need from the physics and vice versa. So it's always a mess. Okay, so you don't have a sense. So you have a sense of how to diagonalize a definite matrix, but you don't have a sense of what happens to a positive definite matrix as it evolves or as it changes through a symplectic transformation.
Yeah, not really because uh and this was I think one of like I was trying to add an application in my original thesis with some like symplectic capacities as like Maurice de Gausson said in his book. There's the notion of symplectic capacities, and you
Yeah.
can have lots of inequalities on them. I was trying to do something like that with the symplectic eigenvalues for like corresponding to a phase space ellipsoid and a phase space cylinder, and trying
Mhm.
to do some sort of non-squeezing between them, and then doing like constraint dynamics with the Dirac constraint terminology and all that. But the problem was the eigenvalues, the way they like change. You can't, upon like a transformation, is something you can't like keep track of. Like for example, if you have A and B, and
Yeah.
each of them have their symplectic eigenvalues. Now A and B, they could be in one giant block of a symmetric matrix. But if you have two symmetric matrices A and B, which have individually their symplectic spectra, then when you like put them in a block and find a common symplectic transformation matrix, it's not very clear that you're going to preserve some sense of ordering.
Mm.
And
Yeah.
that's I think one of the challenges. So,
So let me ask you a simpler question.
mhm.
Have you ever seen, if I think about, just one degree of freedom, so a sort of a two by two, a two-dimensional symplectic vector space, right? The only symplectic transformation there are the one that are volume preserving. So you sort of can stretch and shrink in one side and you can rotate. And that's basically it. That's all that a symplectic transformation can do in two by two. What can it do in a four by four? So it's clear that in each independent degree of freedom, it can stretch and shrink and it can rotate. But what are the type of transformation that can happen across degree of freedom? And do you have you ever seen that mapped so that I can get an intuition for that?
I think they talk about. But I think the problem is all the examples with that stuff. With that kind of mapping are like in quantum information, and I think they only like do work with qubits there, and
Yeah,
that's
no, no. As I said, I
simplest
just want
case.
to do it
So
in classical mechanics and
no,
not
no,
not
not really.
quantum.
Yeah, yeah, not really. Haven't seen. But but if anything, it all has to go back to factorization, because like once you have a symplectic matrix, there's a certain sort of special factorizations you can do with that you can't with any general one. And so all the properties which are unique to symplectic transformations are in that factorization. Definitely look at the factorization. I'm not myself aware
Okay.
of like right
Yeah,
now.
because that would start giving me intuition of what happened to the uncertainty.
No, no,
Right.
no. Like all this is all mathematical, and the last thing mathematicians care about is giving an intuition, unfortunately. So,
Yes.
like many of
That's the
them would
problem.
hardly say that the P's and Q's are like the momentum and position even. So, and if you're a physics person, have taken Hamiltonian mechanics, then you come to appreciate that, oh, okay, this is actually preserving the Hamilton's equations of motion in that form. But
Mm.
otherwise, it's difficult. Yeah.
So, Jesus, the book that we're referring is the book from Maurice de Gasson. Do you remember the title, Rudra?
Applications of quantum mechanics, I think. I also sent it on the chat one time. Or I
Let
can
me see.
email you. I just
Well,
have the call.
they're asking me on the YouTube chat.
Oh,
So,
okay,
but
okay.
but it should be foundable by Maurice de Gasson applications, and maybe I can find it just very
Yeah, it
very
has like
quickly.
a blue and black, blue and gray sort of cover. Let me find if I have it on my.
Uh, is it the symplectic geometry and quantum
Yeah, yeah,
mechanics?
yeah, yeah, that one.
All right, so it's Symplectic geometry in quantum mechanics, advantages and application. Operator theory, functional application. I'll put the, let's
Yeah,
see
yeah.
if it
That's good.
survives. Yeah, there you go. There is an Amazon link in, so we make advertising for, yeah. Okay, so now the other thing that this may or may not be related to is so one of the things that happens in let's put it like this. The symplectic geometry, the way that we recover it, is again related to the existence of an invariant entropy, and then the areas and volumes that are defined by the symplectic form come from the entropy. And so there is a strict connection between the entropy and the symplectic form. Also, if you look at the space of essentially distributions, classical distributions, or the space of mixed state, you can do information geometry, and you have a Riemannian metric, which is the Fisher-Rao metric. There is a classical one and a quantum one. And a little known fact, but both of those Fisher-Rao metrics are minus the Hessian of the von Neumann entropy in the quantum case and the Gibbs-Shannon entropy in the classical case. So there is a very strict connection between, again, the entropy and this Riemannian metric. Now, in the quantum space is a special space because it's a Kähler manifold, meaning that it has both a symplectic structure and a Riemannian structure. They are related in basically in a way that you can take the Riemannian structure and multiply by a J, like you were doing somewhere here, and then you get the metric. So the two things are related to each other. Exactly. So
Yep.
I'm trying to understand how I can essentially refine the same relationship between some type of symplectic form and some type of Riemannian metric in the classical case, because I haven't seen it, and I'm 100% sure there has to be some connection between the two things, but I haven't seen it. And given that here we are doing some of the tricks of looking at like a lot of things on the Poisson bracket side and on the quadratic form side are things that are sort of reminding me of all these things. So I don't know if you have any insight that can help me navigate this puzzle, essentially.
Yeah, I mean, the thing with the HQ was that it, like given some function on your space, which is an observable, you can always define such a Hamiltonian vector field, for example, by just taking the interior product and then setting that equal to like the one form corresponding to that function.
Right.
And the only thing that like happens here is we're given some bilinear from the beginning. Like our vector space had it, like we had to define it. It wasn't coming from something. But so your question would be to see that given some symplectic, can we get like a function like that? That has to do with, because if we take omega of the interior product of omega with that x, you get like some df. Now you can only recover like an f from the df, which is you can only get a zero form from the one form, depending on like how exact, like what the exactness is and things like that. So I think that will have to do with the topology and the space
Right. So
in
I'm trying to understand it first, in the completely linear case, right? And if I have a linear space and I have a metric tensor, then the metric tensor is just a quadratic form in the linear space.
Yes, yes.
Right. And so here we have a symplectic form on one side, and we have essentially what is becomes a metric on the right side. And then what I'm doing there is I'm doing a transformation of one side of the vector, and then which isn't that the form that you would have in a Kähler manifold? Let me go back
Yes,
and
yes,
okay, it
indeed,
is. Yeah.
because
Okay.
the HQ would be the J, the compatible almost complex
Yeah.
structure.
Okay. Very good. So we are on the same page. Yes.
We can
So
we can always, given some manifold, we can always define the symplectic two form by the like going from like the tautological one form, which has like a basis invariant construction. Like you can start with, I think, the tangent of the the tangent
right.
space, and then like just keep pulling back. There's a construction. Again, I have references for all
Oh,
these things.
yeah, wait. Okay, so but let me think. So both U and V's are vectors, they're not covectors. So the HQ would have to be a map from a vector to a vector.
No, in this case, I mean, HQ is actually like in the general setting, it's going to be a vector field. So because like
Right,
if we go back
HQ is mapping a vector to a vector, right?
in this, yes, in this case, yes, it's a
Right.
linear map.
It's a linear map. And so that would be the sort of the
The
J
only
that
problem is, yeah, the only problem is this is a vector space. So the distinction between the tangent of the vector space and itself, it's there's no distinction because it's all the same. It's just
right,
a flat
exactly.
vector
It's
space.
a simpler case. I'm perfectly happy in understanding
Yeah.
that
Okay.
case.
Okay. Okay.
So So let me understand, what is the requirement on HQ such that you have this relationship? This is what are you when you map? So you basically say, if I have a quadratic form HQ, sorry, if I have a quadratic form phi Q, I can always find an HQ such that I can write this. That's the idea.
Yes, and you can show it's unique by the non-degeneracy of the omega.
And it's unique by an non-degeneration. Okay. Okay, so I can always do that.
And
Okay.
even if your manifold doesn't have an omega, you can always get an omega from the tautological one form construction.
No,
So,
I will have an omega because as I said, I have an
okay,
entropy
okay, okay.
defined and I know that there is a definition of the omega, right? And I have that. And then I should also have the G because I have the Hessian of the entropy. And so I know I will have both the omega and the G. And now you're saying, well, if you have an omega and a G, you can always find a linear map such that you
Yeah,
can write this. Huh.
yeah, yeah, yeah. Yeah, since
Okay.
both sides of your equation are going to be non-degenerate, like that map is like well defined, because you can think of like the omega as like maps vector, like an isomorphism from vectors to like covectors, and same with like the
Yes.
G. So it makes sense. You're not losing any like dimensionality on any side.
Okay,
It's
but
well defined.
okay, so we're still talking about finite dimension, right? It's not clear that I
Yeah,
can do
yeah,
this
yeah.
in.
I'm just saying that like the you're not losing anything because of a non-trivial kernel, for example,
Yeah,
on
yeah, yeah.
either
But
side.
the problem is that the G is defined in the space of distribution, which is infinite dimensional. So, okay.
Yeah, that will be a
Okay, but at least there was a little bit more. There is a question in the chat. What does one even need a metric on phase space in classical mechanics? It's not in phase space. It's on the space of the probability distributions. I mean, metric would be important on configuration space to tell distances, but yeah, it's basically an entropic measure of how two distributions are distanced from each other. And typically in a Bayesian framework, it's like how much you can mistake one distribution from another distribution. That's basically how it works. In my case, I think of the distance in this way. You have two distributions. You make an unequal mixture of them, and you see how much the final entropy is different from the average entropy that you've put in. If there is no entropy increase, the two things are the same. And if the two things were, let's say, disjoint, completely different, then the entropy goes up by 1 bit. And so that increase of entropy tells you how far one distribution is from the other. And it's not a distance, but it's a divergence. It's a Jensen-Shannon divergence. But locally, it recovers the Fisher-Rao metric. So yeah. So that's kind of my problem, is that the metric right now, I have it on the space of distribution, while the symplectic form, I have it on the space of points. And I need to write a symplectic form on the space of distribution, such that given two variations of distribution, I will have some notion of symplectic form there. And this is Rudra, where I go back to the point, I need to understand how to extend these things to field theories, to space of distribution, such that then I can define an information entropy that is consistent with all of these things. Because we're able to, so I'm trying to create a formalism for which you have essentially spaces of ensembles without knowing whether you have a classical ensemble, a quantum ensembles, and ideally without even knowing that I have an ensemble that comes from a field theory. And the idea would be to write these, Poisson bracket commutator in some sort of general way against this general space, so that we can have sort of a generalized Hamiltonian dynamics that then when you have a classical space, a quantum space becomes the instance. But we have generalized all the basic theorems and things at the upper level. So the relationship between the entropy, the metric, and the symplectic form is always the same, regardless of the theory that you have, right? That's basically what I'm trying to do. So. Okay, so I am absolutely satisfied by this. Thank you so much. If there are other questions from other people, we can completely open up to question. Again, this to me is really a treat, because these are things, as I said, that I've been trying to look for some insights for a long time, and I can't learn everything about everything. So finding people like Rudra that has looked at these things and having this discussion, to me, it's like saves me months of work, essentially.
On it, if I had like the funding and the backing, I could actually explore this on my own. But the problem is I have a PhD offer, but there's no funding, and I'm not. It doesn't motivate me anymore to work on these on my own.
We are in the same boat. Like if I had the funding, I could, I could. Yeah, that's basically the issue. Like there isn't somehow the way that the incentives are set up, doing this kind of like low level understanding, and let's put everything, it's especially in the US, there's basically no funding for foundations, and
Yeah.
but yeah, I think this is the work that needs to be done. Like we can't. Like how are we going to do quantum gravity if we don't even have the right math to do these type of things for classical field theory? Like not even for classical field theory, I wouldn't know how to do it precisely, right? And anyway, yeah, yeah. Anyway, if there are no questions from the chat or from Zoom, we can probably say bye to Rudra, also because it's probably late for you at this point.
It's fine. It's not too late. I think it's just
Not too late.
9:45.
Not too late.
I mean, anything to like keep me away from my thesis, because it's just been going on.
Yes, exactly. So that we can get distracted. Okay, so I don't see any questions, so we'll close it up. Thank you everybody for the attention. And if you are looking at this later, you can leave comments, questions in the comments, and we'll try to see if we can give you an answer. Thank you, everybody. Let's see you next time.